If you've read the first part of this chapter, or if you looked at the first few videos on this chapter, you should hopefully have this idea that if there is a resultant force in a system, then there is an acceleration, and the acceleration happens in the direction of the resultant force. And that works backwards as well. If you've got something which is accelerating, there must be something causing it to accelerate, and the thing causing it to accelerate is a force that is acting in the direction of the acceleration. So you can ask the question, if we have this overall force, what's the acceleration? And you could ask the question, if we have this acceleration, what is the force that's causing it? Okay, and they're linked very simply by this little equation here, which is Newton's second law of motion, and it's that force equals mass times acceleration. Now, a little bit, unfortunately, they've put all this in bold here. If you remember, the notation should be that if it's a vector, then it's in bold or underlined, and if it's a scalar, then it's not. So I like to write it like this: F equals ma, because the force and the acceleration are the vector quantities. And you can see that they're linked almost as simply as can be. You take the mass of the object that is accelerating, you times that by the acceleration vector, that gives you the force vector. And obviously, if you know the force vector, then you can work the other way around. Now, in this, oh, and I should throw in as well at this point, we've had the example I've discussed previously of the weight of an object. You've perhaps heard that we get weight wrong. When I say I weigh this many kilograms, what I really mean is I've got a mass of this many kilograms. Mass is measured in kilograms, force is measured in newtons, and weight is a force. So the weight force is the force that my weight is the force that I'm exerting. If I sit down on a chair, the force that I'm exerting on the chair is my weight, and that is the weight caused by gravity. Okay, so gravity is doing the acceleration, and little g is the letter that we give to gravity. 9.8, remember that from chapter 9 is the number. So 9.8 times my mass gives you my weight. Okay, and that's why people say you're weightless in space. You're not massless. If I have a mass of 80 kilograms in space, I still have a mass of 80 kilograms, but there isn't a gravitational field exerting a gravitational acceleration, so there's nothing, your weight is zero because it's mass times zero. There is no gravity. And on the moon, your weight is different even though your mass stays the same, because the moon is pulling with a different gravitational force. Okay, so F equals ma is the same as W equals mg. That's a quick way of converting, well, that's the only way of converting mass to weight. So this looks like the simplest possible equation, and to start with, absolutely is. Find the acceleration when a particle of mass 1.5 kilograms is acted on by a force of 6 newtons. So guess what? F equals 6, m equals 1.5, stick them in there, there's your acceleration. It's important to note here really that you've got to watch out for your units. If mass is in kilograms and force is in newtons, then your acceleration comes out in meters per second, and this is this idea of SI units. If your acceleration is not given in meters per second, but is given in kilometers per hour, you need to convert it. And if your mass is not given in kilograms, but is given in tons or grams, you need to convert that as well if you want your resultant force to be in newtons. So just make sure you've got everything in SI units before you stick the things in the equation. But that really is as straightforward as it can get. Example 5. In example 6, we've got something a bit more familiar. We've got these 4 forces, going left and right and up and down, and it says, in each of these diagrams, the body is accelerating as shown. Find the magnitude of the unknown forces. So this object here is going to the right 2 meters per second. So it's got a mass of 2 kilograms. The weight force then must be 2g. Usually what would happen here is that this object would be sitting on a surface, right? So we've got 2g pulling down because the mass is 2 kilograms. The surface provides a normal reaction force, and because there's no motion going on vertically, that normal reaction is going to be 2g as well. So the vertical direction is pretty boring, there's no acceleration, but this thing is maybe a car moving along a road, or a toy car moving along a table, or something like that. We've got a force pulling it this way, and we've got a resistance force, which might be the total of your air resistance and your friction pulling it backwards. Okay. Now, if you're having an acceleration, an acceleration, by the way, usually goes on diagrams with a double arrow to show it's an acceleration, not just a velocity, of 2 meters per second, then what's the driving force that your engine's putting in order to provide that acceleration overall? Okay, so it's having to overcome this resistance force and still keep it accelerating. Well, the overall force horizontally is x minus 4. So, as usual with an equation, F equals ma. So write down your little shopping list. F equals x minus 4. M equals 2 kilograms. Acceleration equals 2 meters per second. Okay? So, this notation I don't really like because R usually stands for resolving. And resolving I like to think of as when you say the force is going right equal the force is going left, that is balancing out the forces. I just like to say horizontally apply F equals ma, but certainly a horizontal arrow is enough to say we're considering what's happening horizontally, and you need to put this in because if you don't, the examiner can't see where your equations have come from. So horizontally, applying F equals ma, F equals this, M equals this, A equals this. So we'll put it into the formula, x minus 4 equals 2 times 2, okay? So x equals 8. Vertically, now I would say we're resolving now because there is no acceleration going on vertically. So resolve, and we've already done this already on the diagram, but according to their things, we've got y equals 2g, or if you like, y minus 2g equals 0, because there is no overall force. So there we go, y equals 2g. You could say that's applying F equals ma, because the acceleration is 0, so y minus 2g equals 0. Whatever you do, you need to think of the horizontal motion, you need to think of the vertical motion. Think of those two things separately. You need to tell the person reading it you are thinking about the horizontal motion with some sort of horizontal arrow symbol. You need to tell the person reading it you're thinking about the vertical motion with some sort of vertical arrow symbol. If you're applying an equation, you need to tell us what it is. If you're doing something else, you need to tell us what that is. And then part B is exactly the same idea. There's just one more force going in there, okay? So 4G plus 20 newtons is the reaction force. Now, it's perhaps just worth pausing there to have a think about that. If you are sitting on a chair and somebody puts their hand on your head and pushes downwards, that's what's happening here. Look, there's 4G going down and then somebody's pushing downwards as well. The reaction force from the chair changes, okay? If you had an object sitting on a surface, it has a weight, there is a reaction force. If you attach a string to the object and pull upwards, but not enough to lift the object off the chair, then the reaction force changes then as well, okay? And sometimes people don't like that one. People think, well, if there's an object sitting on a chair that has a reaction force, why should the reaction force change? Just think about it as if you are, here's you, this is little stick person you, and you're carrying some heavy books or something in your hand. Those books are pushing down and you're providing the reaction force. You're lifting those books upwards. If somebody were to attach a rope to that parcel of books and pull upwards, they will be taking some of the weight off you. The books have still got the same weight, but the force you're having to provide to stop those books falling down isn't as much. Okay, that person will be sort of lifting a bit of the weight off. So that's the way to get an intuition for why that reaction force should change if I add another vertical force in there. Some people find that difficult to see at first. Some people find it completely obvious, and it's just down to the way your brain works. Don't worry, whichever way you're seeing it, you'll get into the habit of seeing it that way. Okay, so there we go, section 10.3. And next video we'll see section 10.4.